In this section, we talk about basis and dimension. We've talked about basis a little bit. We defined it. And that's why I've written the definition again for you here just to help revisit. I want to look at different ways to find a basis for a subspace. We know that we can find a basis for an eigenspace by looking at the eigenvectors of a matrix. But a little bit more expansion on what a basis is, how we find it, and what things we should look for, and how this pertains to our unifying theorem. So we have that a basis, or a set here, B1 through Bm, is a basis for a subset S if B spans S and B is linearly independent. Okay, so it's a linearly independent spanning set. For example, the vectors 1, 0, and 0, 1 are the basis vectors for R2, right? Those two vectors together span R2. They're all we need to span R2. They're linearly independent, and they span, right? We can come up with basis vectors for all sorts of different kinds of sets, but the main idea is that it's the kind of easiest way to write a set of vectors, right? And all the combinations of them. This is a theorem that we'll use here, theorem 4.9. Let B be the set of B vectors, and they're a basis for the subspace S. Then every S in S, every vector in my set, my space, can be written as a combination of B vectors. So S is S1, B1 plus all the way through SM, BM, which of course just means that the span of my basis vectors is my subspace S, right? Again, that's basically just rehashing kind of the definition. It's a set of linearly independent spanning vectors. Right? And what I want to do is look at an example and kind of ways, how do we find a basis for a set of vectors or a subspace? How do we do that? How do we find a set of basis vectors? Well, there are kind of two ways we do this, and one of them requires the use of this theorem here. Let A and B be equivalent matrices, then the subspace spanned by the rows of A is the same as the subspace spanned by B. So what this means is if we have two equivalent matrices, we can use one to tell us information about the other, and in the context of basis, right, and subspace. So, for example, and continue on this page here, what does this look like? What does this look like? Let's look at an example. Well, not an example yet, I'm sorry, ahead of myself. I want to kind of outline the steps of these things here. Basically what we'll do is we'll take the rows, or take the vectors, let the given vectors form the rows of A. And then what I want to do is transform A into an equivalent matrix B, into echelon form as an equivalent matrix B. And then the non-zero rows of B will give me a basis for S. Okay? So I'll show you what that looks like. I'll put this on the next page as well, but let's look at an example finally here. Say I have S as the span of these three vectors, and I want to find a basis for this set, this basis. Okay, I want to find a basis. I'm going to use those three kind of guidelines here. I want the given vectors to form the rows of A. So I write A where the vectors are the rows. Okay, so there's A. And then I transform A into echelon form. So I plug this into a calculator. I find the reduced form. You could do RREF or just REF, the echelon form. I do echelon form here. I get the vector, or the matrix, B, is 10, 0, 26, 8, 0, 10, 22, 6, and then a row of zeros there. The non-zero rows of B give a basis for S, the non-zero rows. So that's the first two rows of B right there. They will give me a basis for S. So my basis for S is really those two rows, and I just kind of rewrite them as column vectors. That's the first way, basically, we see to find a basis. Right? It's not necessarily my preferred way, right? I have to think about making these, what I've originally written as column vectors, into row vectors, and then reduce a matrix, and then otherwise it's relatively easy after that, right? the vectors that I have left over are a basis. What I want to show you is a kind of a different way here. But first, let's look at another theorem. And we're going to use this theorem to help us kind of look at the next method to finding a basis. If A is a matrix given by A1 through AM, those vectors, and B is another matrix, B1 through BM, these matrices are equivalent, then their dependence that exists among the vectors that make up A also exists among the vectors B that make up B. All right? So basically what that says is if I have a matrix and I reduce it, right, or if I find an equivalent matrix, if I find that a couple columns are linearly independent in B, then those same columns in A will also be linearly independent. Excuse me. Okay. For example, let S be the span of these three vectors. And in fact, those are the same three vectors as before. So I'm not going to treat them as rows this time. Basically, just what I want to do is put them in a matrix. Let's write A here is the matrix where those vectors are the columns, and then reduce it to an equivalent matrix B. And we see that some of these columns then are linearly independent, right? These first two columns are linearly independent. The third is a combination of those first two, okay? In fact, we have that 2 times B1, 2 times the first column, minus 1 times the second column will give me the third column, that B3. Okay? That dependence is shared with A as well. So if I take 2 times A1 minus A2, that's the same as A3. Okay? The dependence is shared between the two because they are equivalent matrices. Now what that means in terms of basis is really the first two pivot columns of B, or the pivot columns of B, in this case the first two columns of B, those corresponding columns in A form a basis for the set. The basis for my set, because those two first columns are linearly independent, then I have a basis, and that's the first two columns of A. That forms a basis for my set. Okay? And I want to kind of treat this like I did the first example, where I kind of went through some bullets and walked through that process. I just kind of jumped right into this one. Let's go back a little bit. This is the second method for finding a basis. Basically what we do is we use the vectors to form a matrix A. To form the columns of A. Transform A into an equivalent matrix, right? Say B, and we use echelon or row reduced echelon form to do that. Then the pivot columns of B will be linearly independent, and the non-pivot columns, then everything else will be linearly dependent. So from there, what we're able to do is say the corresponding columns of A, the columns of A that correspond to the pivot columns of B, will form a basis. The pivot columns of B form a basis for S. Okay, let's do another example here. And I want basically the same as what we just did in the last example. You can go backwards if you like, but hopefully using these three bullets. Unfortunately, I don't have enough room on my next page to copy this back, so if you want to go back and forth, you're more than welcome. But let's see here. Suppose I have S as the span of those four vectors. Each of those vectors is in R4, so I'm looking for a basis for the span of those vectors. I want to see the shortest, most convenient way to write that set of vectors. Okay? So what I do is I basically write those vectors down in a matrix. Write them down in a matrix. A is the matrix formed by those vectors being the columns. And then what I do is I reduce. I find matrix B as the reduced form. I plug this into a calculator. It gives me the reduced form. The pivot columns here of B, and the corresponding pivot columns then in A, right? So the first and third columns of A will be my basis vectors, but let's write a little more. These pivot columns are the first and third columns. Those are the same pivot columns that I will look at in A. So really, the basis for my set is the two vectors, the first and third vectors of A, because those two are linearly independent and they will span my set. Everything else is linearly dependent. So those two vectors are all I need to come up with all the vectors in my span. Right? They form a basis. Now, another bit in this section that we talk about is what we call dimension. Okay? The dimension of this basis, or the dimension of this set S, is just 2. And that's kind of a weird thing. The dimension of S, or dim S, is 2. All that is the number of vectors that form my basis. That's it. And this is kind of a useful thing. We're able to look at a couple shortcuts by identifying what the dimension of a space or a subspace is. So basically what we have here, S, forms a 2-dimensional subspace for R4. 2-dimensional subspace for R4. Let me write that down. 2-dimensional subspace for R4, right? Those vectors that I was working with are in R4. So what I have then is a 2-dimensional subspace. That's the simplest way that I can write the vectors in my span. I want to look at another example here. Some observations that we have. Let U be the set of vectors U1 through UM be a set of vectors in a subspace. The first observation we have is that if U is a linearly independent set, then U is a basis for S, or it can be made into a basis. Okay? So we kind of saw this maybe a little bit in the last example or two. In fact, more the second observation that we'll see. But basically what that means is if I have a vector here, say the vector 1, 2, that's a vector in R2. And by no means does it give me every vector in R2, right? I can't come up with every vector in R2 with that vector. It does not span R2. It's linearly independent. It's by itself. Then it's either a basis for R2 or it can be made into a basis by adding a vector. Well, I need to add something to this. And really, if I just add the vector, say, 0, 1, then this set should span R2. The vector I had was linearly independent, but it wasn't enough to give me a basis, right? I had to add something to it to form a basis. The second bullet is what we saw in the last example, where basically the set that I had was kind of too much. The basis was able to be made from just kind of a collection of the vectors in my set. So let me write that out for us here. If U spans S, or the span of U is S, either U is a basis, or U is a basis for S, or vectors from U form a basis for S. Okay, so that means I can take some away. Say I've got the 3 vectors here in R2, and the span of those vectors is my set. Span is S. Right? I know these first 2 vectors, 1, 0, 0, 1, from before, those are my basis vectors in R2. Those are the only 2 vectors I need to span R2. They're linearly independent. They can collect everything in R2. 2, 3 is redundant. It's linearly dependent. So basically this set here, I find a basis. I could reduce this, right? But it's already pretty much in reduced form. These 2 vectors, when I collect those 2 by themselves, they form a basis for my set. I don't need 2, 3 to do that. All I need is 1, 0, and 0, 1. Okay? Let's actually kind of work through this. Now, if I want to find a basis for this set, so that a basis for R3 from this set, basically. I have a set of 2 vectors here, both of those vectors in R3, and I want to form a basis for R3. This is very similar, but basically what I have to do is add instead of take away, right? I don't have redundancy. This is similar to the first bullet. I need another vector to span R3. I just don't know what that vector is. Right? But if we consider these two vectors, take the two vectors that I'm given, and if I add to those some of the basis vectors for R3. Well, if the basis vectors for R2 are 1, 0, 0, 1, then the basis vectors for R3 are the three vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. The set of these vectors definitely spans R3. In fact, these three vectors alone span R3. I don't need the other two. But maybe I can just add one vector, right? I'm saying to expand the set that I'm given. Not just write a whole new set, right? I want to add to the set that I'm given to span R3. So I basically have to figure out if the two vectors I'm given are linearly independent or dependent, and kind of then what other vectors I need. But what we can do then is treat this new set, including my three basis vectors, as a matrix, and reduce it to see where the dependence lies. Are the first two linearly independent? Can I use some of the other vectors? Let's see what happens. When I reduce to an equivalent matrix, just the echelon form here, I get this following matrix. And we see that I have pivot columns in the first, second, and fourth columns of this matrix. So that means the first, second, and fourth columns of A will form a basis for R3. The subspace that I'm working with here is in fact the entire set. So what I do is just write down those three vectors. Really the only vector that I had to add to span R3 was this fourth vector 0, 1, 0. That will span then my set. So those three form a basis for R3. I write them down. This set spans R3. It's the simplest way that I can span R3 given those two vectors that I already had, right? Of course, I could just write, the basis vectors for R3 are 1, 0, 0, 0, 1, 0, and 0, 0, 1. But I wanted to use the two vectors that were given, okay? Now, the dimension of this subspace, well, the subspace is the entire three-dimensional space, so the dimension should indeed be 3. Dimension of R3 is 3, and that makes some intuitive sense. In the previous example, we weren't really working with all of R2. You can go back a little bit. The number of vectors in my basis that form my basis is the dimension. Okay, one more kind of example here to work with. Find a basis for the null space of this matrix A. Okay, null space. We've got to remember what null space means. Null space is the set of solutions to the problem AX equals 0, right? So the null space of A is all the vectors that make up the solutions to the system AX equals 0. So I augment my matrix A with the 0 vector. I reduce, and this will give me then the vectors that form the null space. Oops, sorry, a little too fast. The vectors that form the null space of A. I'm just solving this homogeneous system that gives me the null space, right? So what I see here is the third column is a non-pivot column. X3 is S1. X2 and X1 I can write as then multiples of S1. Okay? So my solution vector is S1 times minus 3 halves, 1 half, and 1. Okay. What we typically do, again, we saw this with eigenvectors, is when I want to write this in its simplest form, I want to factor out a 1 half, divide S1 by 2, and that's the same as having minus 3, 1, and 2 as my null space. Really, there's only one vector in my null space, right? There's only one vector. The span of that vector forms the null space of A. Okay, so all combinations of minus 3, 1, 2 solve my system when I set it equal to 0. That lone vector there forms a basis for the null space. The null space of A is the span of that one lone vector, and that forms a basis for the null space of A is just that vector by itself. Now the dimension of this space is 1. Dimension of the null space is just 1 because there's only one vector that forms my basis. Okay? So, and that I guess maybe makes some sense or doesn't. This also has another kind of corresponding terminology to it. We call this the nullity of A. It's the dimension of the null space. Okay? So just another little bit of terminology, another quick definition for you. The nullity means the dimension of the null space. So we'll talk about nullity a little bit more in the next section. This corresponds or adds a little bit to our unifying theorem. Okay, what that says is now A forms a basis for Rn, right? If we're in all these kind of perfect scenarios, I'm in a square system, I have n linearly independent vectors, then they span my set, A forms a basis for n, those all mean, for Rn, those all mean the same thing. We'll expand on this a little bit in the next section. Thanks for watching.